Titration curves for amino acids are one of those things in biochemistry that look way scarier than they actually are. So let me take you through a step-by-step method for drawing these titration curves for the non-ionizable amino acids, as well as the harder cases where you have those ionizable side chains. So we're talking the basic and acidic amino acids. I'll show you how we can draw these curves, as well as how we can think about and appreciate what's going on at each step along the way. Before watching it, you should have a solid grasp on pH, acid-base chemistry, pKa, these things. So if you need to go ahead and watch the review video, do that. And you should also have a solid grasp on the amino acid basics. So let's dive in. Speaking of amino acids, each amino acid is going to have at least two ionizable groups, two parts that can give or take protons and thus be neutral or positively charged or negatively charged, depending on whether they are protonated in their neutral state. The first of these is the N-terminus. So at the N-terminus, you have this amino group, which can be neutral if it's deprotonated, and if it's protonated, it can become positively charged. So you're always basically going to have the nitrogen bound to at least two hydrogens, but it could grab a third, and this would make it positively charged. At the C-terminus, you have a carboxylate group, which can be protonated and thus neutral, or it can be deprotonated and thus negatively charged. So you have these two ionizable groups on every amino acid. Now, every amino acid also has that side chain, that R group, and some of these are ionizable and some of them are not. When we focus on the charged amino acids, we typically think about the acidic ones as being your aspartic acid or which can deprotonate to make aspartate, which is negatively charged, as well as glutamic acid, which deprotonates to get glutamate, which is negatively charged. We also think about, for the basic ones, we think about histidine, lysine, and arginine, all of which can protonate and thus be positively charged. But when we think about things, when we think about the side chains that actually have ionizable groups, we also need to consider a couple more. And so the couple more additions that we're going to add when we're talking about the pKars, so the pKas for those side chains, we're going to add a couple more onto our list. So we're going to add cysteine, and we're going to add tyrosine. And these two, basically, they have pKars that are listed, so you can find them in a table. You'll see that, so tyrosine has a pKar of 10.1, which is actually very, very high of a pKa, and cysteine has one of 8.3. So these are very high pKas, but these pKas, basically, they can happen, they can be measured, and so we can draw titration curves for them. You might be wondering, okay, well, why is tyrosine considered acidic, but lysine is considered basic? If lysine has a pKar of 10.5 and tyrosine has one of 10.1. Well, you have to remember that the pKa is always going to be for the acid. And so for a lysine, when it's going to be in its positive state when it's in that acidic form, whereas tyrosine, it's in its neutral state when it's in that acidic form. So tyrosine, when it deprotonates, then it's going to be negatively charged, whereas lysine, when it deprotonates, it's going to be neutral. When we refer to something as acidic or basic, we're referring to it in its neutral state. So thus we think of tyrosine as being acidic and lysine as being basic, because we're thinking about them in their neutral form. So when we're talking about the acidic R groups, what we're going to be thinking about are our classic ones. So we have our aspartic acid or our aspartate. Remember that it can be abbreviated D. We have our glutamate or our glutamic acid, GLU, which we can abbreviate E. Then we have our couple extra ones that we're going to add in here. We have our cysteine, abbreviated C, and we have our tyrosine, which we can abbreviate Y. And we're not going to include threonine or serine because they have pKas that are very, very weak. So we're not going to worry about those ones, but we will include cysteine and tyrosine when we're thinking about the ones that are ionizable in terms of things like drawing titration curves. Okay, So now let's talk about the basic ones. So the basic ones, these are the ones that, the classical basic ones. So we have our histidine, which is H. We have our arginine, which is R. And we have our lysine, which is going to be our K. Remember, a special K. Okay, so now that we have these in mind, we can go ahead and look at how we're going to draw titration curves for them. Each time we draw a titration curve, we're going to need a couple pieces of information. We're going to need the pK1, which is going to be for the C-terminus. So pK1 equals C-terminus. So that's going to be your COOH group. Your pK2, well, that's going to be your N-terminus. So that's going to be your NH3 plus group. And then for your side chain, that's going to be your pKr. So your pKr for the R group equals R group. And this is the one which may or not have a pKa. So if you see it doesn't have a pKa in a chart, that's because it's not one of those ionizable groups that we're going to consider. Well, also sometimes you'll see in a table the pi, and we'll show how we can actually calculate this pi. So the pi is the isoelectric point at which net charge equals 0. Okay, so now let's go ahead and look at some titration curves for these. Here's the basic strategy we're going to take. First, we're going to identify the number of ionizable groups. So remember, there's going to be at least 2, the N and C termini, and possibly a third in that R group. This is going to be the number of hydroxide equivalents that you need to fully deprotonate it. Next, you're going to draw your x-axis, extending that many equivalents worth, and label each 0.5 increment. Then you're going to sketch the state of each ionizable group at each increment and label its charge. Remember when you're doing this that the groups are going to deprotonate in order of increasing pKa, so the most acidic first. So remember that the pKa is going to be the pH at which half of it is protonated and half of it is deprotonated. If you're at a pH that's below the pKa, this means that there's more protons available, so more than half of it is going to be protonated. And if you are above the pKa in your pH, you're going to have fewer protons available, less than half is going to be protonated. And because each pH unit is going to be a 10-fold, it's like a log scale, so you're going to have 10-fold less of the protonated form for every increase in pH you go above your pKa. So you can quickly get away from having similar amounts, and this is going to be the idea of a buffering region. And we're going to be able to see this buffering region on our titration curve. To plot this, we're going to plot the points intersecting each half hydroxyl equivalent. So basically, you have your 0.5, your 1.5, your 2.5. At each of these points, this is going to correspond to one of the pHs equaling the pKa. And so remember, when the pH equals the pKa, your concentration of your conjugate acid is going to equal your conjugate base concentration. This is going to be complicated in the fact of our amino acids by the fact that we're going to have those multiple ionizable groups. So we can kind of thinking of having lots of different 2 or 3 HAs and A minuses. But once we plot those points, we're going to draw a flattish buffering zone around that point. So remember, the buffering zone is about 1 ± 1 pH unit. Is going to be where you have enough of the acid to neutralize added base and enough of the base to neutralize added acid. Now what you're going to do is you're going to draw points at each 1OH minus like points, so 0, 1, 2, or 3, if applicable. Remember, only some of them. If you have a non-ionizable group, you're only going to have 2. If you have an ionizable group, you'll have 3 of those equivalents needed. And then you're going to draw these points halfway between the pKa's on either side. And the steepest part of the inflection will be at this point, this kind of like halfway between the pKa's. Now, one of these halfway points is going to be a special point because this is also going to be our pi, our isoelectric point. And so the isoelectric point is going to be the pH at which things are net neutral. And this is going to be the average of the pKas on either side of the zero charge. So it's going to equal the average of the two most similar pKas. And hopefully this will all make a little sense once we actually graph things out. In order to graph things out, I'm going to introduce a little bit of shorthand notation that I'm going to use. So I'm going to be representing an amino acid with this kind of like T, where on your left you have your N-terminus. So this is going to be our amino group. On the right, you have your C-terminus, and then sticking up, you have your R group. A zero is we're gonna be drawing the charge here. We're not gonna, so this is a 0 and this is not an O. So don't be thinking, okay, this is O, so it's gonna be, that means you have a negative charge. If you have your O is gonna be deprotonated. That's not what this means. Right here, we're talking this 0 as not an O. So 0 is no charge. If we have a plus sign, that indicates a plus charge, and a minus sign is gonna indicate a negative charge. We can draw things like this in 3 different sorts of scenarios where we have a non-ionizable R group. So this is going to be something that is most of our amino acids. So the things that are non-polar and the things that are polar but don't have an ionizable side group. Then we don't have to worry about the R group, so we can just kind of like draw a straight line. And then we'll have cases where we have our basic R groups or our acidic R groups. We're going to be talking in terms of hydroxide equivalents. So basically, an equivalent is the amount needed to deprotonate one of the groups. So you might see like NaOH or you might see KOH in equivalents. Basically, those are going to be strong bases. So when you put them into water, they're going to dissociate. They're going to give you a hydroxide ion. The hydroxide ion is going to strip the proton away from the acid. You need 1 equivalence worth to strip away one proton. Because once it takes a proton, well, now it's not a base anymore. So you're going to need enough equivalents to strip off the number of equivalents you have of acidic groups. And in the case of our non-ionizable R group, we're going to have to need 2 equivalents worth. 1 equivalent is going to be to strip off to deprotonate the carboxylic acid group, and 1 to deprotonate the N-terminus amino group. So for some of these, you're going to have to look and in order to determine what order things are going to be going in, remember they're going to deprotonate in order of increasing pKa. So the stronger the acid, the easier it's going to be to pull off one of those protons. And so you're going to pull those off first, and then as you go to more equivalents, and you'll pull off the ones that were harder to pull off. In terms of some of these, it's going to be kind of easy to see which order you're going to go in. So if you have a non-ionizable R group, remember that carboxylic acid group is going to be way, way, way more acidic than this amino group. So the carboxylic acid group is going to have a pKa of somewhere around 2, whereas this N-terminus is going to have a pKa closer to 9 or 10. So what this means is that you're starting off, you always want to start off in your fully protonated state, where you're going to have your N-terminus is when it's protonated, it's going to be positively charged. Your C-terminus, when it's protonated, it's going to be neutral. So you have an overall charge of +1. If you go to 1 equivalence unit, what's going to happen is you will have stripped off all of the protons from your carboxylic acid group, leaving that negative. The N-terminus is still going to be positive. You're going to have an overall charge of 0. What would happen if you go to 2 equivalents? Well, here you're going to have deprotonated your carboxylic acid group still, and now you're going to also have deprotonated your N-terminus. That's going to give that a charge of 0, and so this leaves you with an overall charge of -1. So that's in the case of our non-ionizable R group. What about our basic R group? So think back, and what are the basic R groups that we're going to be talking about? What are the amino acids with the basic R groups? So we're going to have our arginine, we're going to have our lysine, and we're going to have our histidine. Now, for arginine and for lysine, they're going to have R groups that are going to be less acidic than the amino group. And so they're going to have higher pKas than the amino terminus, and so this means that the amino terminus the N-terminus is going to deprotonate before them. In the case of histidine, it actually has a lower pKa than the N-terminus, so it's going to deprotonate before that. So you kind of have the third structure that you'll see with these two is going to be different for them. And hopefully this will make sense in a second. But for the most part, these are all going to follow a similar pattern. When you're in your fully protonated state, well, here, remember, in the protonated state, the basic R groups are going to have a positive charge. That amino group is going to have a positive charge, and your carboxylic acid group is going to be neutral. This leaves you with an overall charge of +2. At one equivalence point, you will have deprotonated your strongest acid. So we will have deprotonated that carboxylic acid group, leaving that with a negative charge and leaving you with an overall charge of +1. Now, when you go to 2 equivalents, you're going to have deprotonated your next strongest acid. And in the case of your lysine or your arginine, this will be the N-terminus. And in the case of your histidine, this will be your R group. In either case, you're going to be left with a charge of 0. Now, when we have a charge of 0, this is going to be a special place because this is going to be where we have our isoelectric point, our pi. And so we'll get back to that later. But this is going to be your pi for your basic group, and for your non-ionizable group, this would be your pi. What we'll see too is that the isoelectric point, the pi, is going to be equal to the pH halfway between the pKas of the most similar ones. Okay, finally, if you add a third equivalence, you're going to deprotonate all of those ionizable groups. And so here now you'll have deprotonated the N-terminus, the R group, and the C-terminus, and this is going to leave you with a charge of -1. Now let's talk about our acidic groups. So what are the acidic groups that we're going to consider when we're drawing titration curves? Right, so we're going to have our aspartate, we're going to have our glutamate, we're also going to have our cysteine, and we're going to have our tyrosine. These are the ones that you typically see having pKars listed. So for anything where you know the pKr, you can draw a titration curve for that amino acid. And if it doesn't show a pKr, then you're typically not going to be worrying about the side chain deprotonating. Okay, so let's consider what we have in this case. What differentiates the acidic ones from the basic ones is that in the acidic ones, remember, acidic refers to it in its neutral form. So it's neutral when it's protonated, and it's going to be negatively charged when it's deprotonated. When we think about the drawing a titration curve or sketching out these skates for something that's acidic, when it's fully protonated, remember, in a protonated state, the acidic groups are going to be neutral. And so we're going to have our amino group is going to be positive, and both of our acidic groups are going to be neutral, both the carboxylic acid group in the backbone, as well as that in the R group. When you add one equivalent, you're going to deprotonate your stronger acid. And this is going to be the one in the backbone. So the carboxylic acid group in the backbone is going to be stronger than the one in the side chain. So this is going to deprotonate first. If you add a second equivalent, well, now you're going to deprotonate that side chain as well. This is going to leave you with a charge of -1. If you add a third equivalent, well, now you're going to also deprotonate that amino group, leaving that neutral. And so you're going to end up with a charge of -2. The exception to this is going to be our tyrosine. So here we have our pKr. So that's for the R group is going to actually be greater than our pK2, so greater than the pKa for our N-terminus. And what this is going to mean is that it's actually going to deprotonate last. So we're going to have 4Y. We're going to actually have it so that at this 2 equivalence point, the one that's going to be deprotonated is actually going to be the backbone. And your side chain is still going to be protonated at this point. But that's going to be the only 2 points where this is going to differ. You're still going to get your backbone carboxylic acid deprotonating first, and you're still going to end up with all of them being deprotonated. But you're going to have this different point at this one place. But you typically don't see titration curves for tyrosine drawn much. It's just like, you should know that it's going to deprotonate last in that case. And so if you were to draw a titration curve for it, you would need to take that into account. So going back to our strategy, let's show how we can draw a titration curve for glycine. So remember, this is going to be one of our non-ionizable side groups. So we're going to have those two pKas to consider. And if we have two ionizable side groups, what is this going to mean in terms of how many OH minus equivalents we need? Because remember, this is going to be our step one. Right, so we're going to need two hydroxide equivalents in order to deprotonate both of those groups of glycine. So we can go ahead and we can sketch out our x-axis. So we're going to make our x-axis so that it's going to extend to include 2 NaOH. So we're going to have 1 and 2, and we're going to want to draw our halfway points. And sorry, I said NaOH, but this could also be KOH. Basically, we're just going to write OH minus equivalents, but you might see sometimes like NaOH equivalents or something like this. Okay, so remember when we have like the 0.5 and the 1.5, the places that were halfway in between equivalents, those are going to be the points that are going to correspond to, we're going to plot intersecting the pKa. And then at the equivalent points, those are going to be where we're actually like fully deprotonated. But remember that the pKa is going to be where you have half of your acid and half of your base. And so we consider the pKa for each of these different ionizable groups. And in either case, the pKa is going to correspond to the half of that ionizable group being protonated or deprotonated without thinking about the other group. So let's just sketch this out to make things easier to see, and then we'll show how we can plot those points on the graph. So let's start about thinking at if we're fully protonated, so we haven't added any NaOH. What's going to happen is we're going to have our N-terminus be positively charged, and we're going to have our C-terminus be neutral. So both of these are protonated at this state. What about at 1 NaOH equivalent? Well, remember that you're going to have your stronger acid deprotonate first. And so if we look at our two pKas, we're going to see that our pK1, so for our C-terminus, this is going to be about 2.34. And for our N-terminus, it's going to be about 9.6. So the carboxylic acid, the C-terminus, is going to be a much stronger acid. It's going to deprotonate first. When it deprotonates, it leaves a negative charge. Now remember that for each NaOH or each OH minus equivalent, you're only going to be deprotonating one group. And so we're still going to have our amino terminus is going to be positively charged. It's still going to be protonated. But when you get up to a 2, you're going to have it so that now that amino group is going to deprotonate as well. So now it's going to be neutral, and your carboxylic acid group is going to be negative. Okay, but now we need to think about what's going to happen at the halfway points in between them, because the halfway point, remember, this is going to be where we have the pH equals the pKa. And this is a value that we know and that we can plot. Let's draw what the states would be at those places. Basically, what you have here is you'd still have all of this would be protonated. All your N-terminus would be protonated at a 0.5 OH minus equivalents. But now you would have half of your C-terminus be protonated and thus neutral, and half of it be deprotonated and thus negatively charged. Similarly, if we go to a peak 1.5 equivalents, well, now all of your C-terminus is going to be negatively charged, but your N-terminus, half of it is going to be positive, and half of it is going to be neutral. And so now what we can do is we can go and say, okay, well, what would the charge states be for each of these? Well, here we would have a +1, we would have a 0, and remember that 0, because remember that's going to be our pi. When we go to our 2 equivalents, well, now this is going to have a charge of -1. And if you go into those halfway points, basically this would have a charge of plus 0.5, and this would have a charge of -0.5. Okay, so those are our different states. And now let's go ahead and let's actually plot them on the graph. So let's start with the pK values that we've given. These are going to be equal to the pH at which you have half of a group protonated and half of it be deprotonated. So remember, when we're thinking about these halfway points, well, that's where we're going to be thinking about when we're kind of at these 0.5 and these 1.5. So we're on step number 4 here. And what we're going to do is basically we're going to find the intersection where the pH equals the pKa and we're at like the half equivalent or the 1.5 equivalent. So for this first point, so we're going to start with our most acidic. So our pK1 is going to be 2.34. So what I'm going to do is I'm going to go over to my pH axis, draw a dotted line over from about 2.34 to half an equivalent. And now this is going to be, sorry, my pencil does not like when I try to fill in circles, but this is going to be your pK1 equals 2.34. Now what I'm going to do is I'm going to do the same thing for the second our pKa group. So this is going to be our N-terminus. I'm going to go over to 9.6, draw a dotted line over. At this point in time, I'm going over to 1.5 units. And this is going to be our pK2 equals 9.60. Okay, so now remember that special region that's going to be around the pKa. This is going to be your buffering region, about +1 and -1 pH units above. Basically, you can kind of just sketch out a fairly straight line around the two of them. And that's going to be kind of like your buffering zone, where if you add a little acid, you'll have enough base to counteract it. And if you add enough base, you'll have enough acid to counteract it. The same cannot be said for the point in which you're in between the point when you're in between the pKas. And this is going to be like your equivalence point. This is going to be where you're going to have a really steep inflection point. And so these are going to happen at your like 1 and at your 2. Basically, once you've fully deprotonated all of the acid, you're not going to have any acid to counteract any added base. And so you're going to get a steep rise if you were to add any more of the NaOH. What we're going to do in order to plot these points is basically you're going to draw a midway point between the two the pHs of the two pKas at that equivalent. And so you can either just kind of like estimate it, or what you could do is you could actually calculate it. So in this case, I could take the pKa, the two pKas, so 2.34 plus 9.6, and then I just average those out, and I get 5.97. Now what I can do is I can go ahead and I can come over to here, draw 5.97, and go over to 1 NaOH equivalent. And this is going to be, that's my 5.97. And then around this point is when we're going to have that really steep region. So I can kind of go ahead and I can just kind of connect these lines. So remember, I'm going to have this really steep part here, and then it's going to go and it's going to be back to this buffering region. And now as I approach the second point, I'm going to have another really steep region. Okay, so this is what our curve is basically going to look like. And now let's find our PI. Well, remember the PI is going to be the point at which we're electrically neutral. And so this is going to be our PI right here when we're at this electrically neutral point. And this is going to correspond, in the case of glycine or any non-ionizable amino acid, basically it's going to be the point halfway in the average of your two pKas. And so this is this 5.97 point that we saw before. So this is actually our PI. So our PI is the point in which we're electrically neutral. Overall, net neutral is going to equal the pH in between the two pKas that are the closest. And in this case, there's only 2 of them. So it's just going to be the average of that N-terminus and of that C-terminus pKa. And this is going to be your PI. So this is going to also be our PI. Okay, if we want, we can kind of, if it's kind of hard for you to see which of these corresponds to which, we can actually just go ahead and label these on our chart as well. So let's just go ahead, and this would be our A. So let's just go ahead and we'll say A, B, C, D, and E. So this would be our A, our B, our C, our D, and our E. So now if I were to ask you, okay, well, what would be the predominant charge state at like a certain pH? Or I were to ask what is the overall charge at a specific pH or at a specific number of equivalents added, well, now you could look at your graph and see this. And we can also do things with the Henderson-Hasselbach equation that we've talked about. But this is how you would draw a titration curve for a non-ionizable amino acid. So that was the easy stuff. Now let's get into a little harder where we have a third pKa to consider, a pKa for our side chain. So things are going to be very similar, except that in this case, we're going to have a third equivalence point. We're going to need 3 NaOH equivalents because we have those 3 ionizable groups. So if we look at our number 1, identifying the number of ionizable groups, well, here we're going to have 3. We're going to have our N-terminus, which has a pKa of 8.95, our C-terminus, which has a pKa of 2.18, and our R group, which has a pKa of 10.53. So if we, so we're going to need 3 NaOH equivalents, so we can go ahead and we can write our x-axis going out to 3 OH minus equivalents. And remember that we're going to want to draw the 0.5 marks as well, because this is going to be where we're going to be corresponding to to our pKas. So 0.5, 1.5, and 2.5. Okay, so now let's sketch out what's going to be happening at each state. So remember, we need to think about this in terms of their increasing acidity. So remember that we look to the pKas to tell us about the acidity, and the lower the pKa, the more acidic something is, the less NaOH it's going to take to pull it off. So the more acidic ones are going to deprotonate first, the less acidic ones are going to deprotonate later. So how can we put these in order of increasing pKas? Yes, so first we're going to deprotonate our C-terminus. It has the lowest pKa. Then we're going to deprotonate our N-terminus. It has the next lowest pKa. And then we're going to deprotonate our R group, which has the highest pKa. So we can go ahead and we can sketch out the charge states at each of these. So in our fully protonated form, remember our N-terminus is going to be positively charged. Our R group is going to be positively charged, and our carboxylic acid group is going to be neutral. If we go to 1 NaOH equivalent, now we're going to deprotonate our strongest acid, which would be our carboxylic acid in our C-terminus, and the other 2 are still going to be protonated. But if you go another NaOH equivalent or another NaOH minus equivalent, well, now you're going to deprotonate your next strongest acid, which in this case is the N-terminus in the backbone. When it's deprotonated, it's neutral, and then your side chain remains positively charged. What happens if you go out to a third equivalence? So now basically you're going to deprotonate everything. And so this is going to be deprotonated and neutral, deprotonated and neutral, deprotonated and negatively charged. Now let's go ahead and think about what happens halfway in between each of these points. And remember, when we're talking about halfway in between each of these, we're talking about the points at which we have the pKars or the pKa values. So in this case, if you're halfway between your 0 and 1 equivalent, you're going to have half of your C-terminus be deprotonated and half of it be protonated. The other 2 groups are going to be fully protonated. When you go up to the next one, you're basically going to have it so that all of that C-terminus is now going to be deprotonated, but now only half of your N-terminus is going to be protonated, and your side chain is still going to be protonated. Then if you go up another, you're basically going to have now your N-terminus is all going to be deprotonated, your C-terminus is all going to be deprotonated, and half of your side chain is going to be deprotonated. Now we can go ahead and we can write out the charge data, each of these. So if you're fully protonated, you'll have a +2. If you deprotonate 1 equivalence worth, you're going to have a +1. Another equivalent worth, you're going to be a 0. Remember 0, that's a special point. That's going to be our pi. And if you go out to your 3 equivalents, well, now you're going to have a charge of -1. If we're at our halfway points, we're going to be halfway in between those charges. So basically, we're going to have a charge of plus 1.5. Remember, this is going to be our average charge. It's like our net charge. So it's not like we have a half charge on one of those things. It's just that we have a 50-50 amount of the ones that are charged and the ones that aren't charged at that specific point. And then we still have, so at this time it's on the C-terminus, and then we still have those two charge groups. So that's how we get our 1.5. For here, we're going to have plus 0.5. And for here, we're going to have minus 0.5. So those are going to be our different ionization states. Okay, so now let's go ahead and let's follow our instructions. So we've done 3. We've sketched the state of each ionizable group at each increment and labeled its charge. Now we're ready to actually plot things. So remember that when we start with the plotting, we're going to go and find the intersection where the pH equals the pKa, and we're at the number of OH minus equivalents, the halfway point in the number of OH minus equivalents for that ionizable group whose pKa we're talking about. So we're going to start with our most acidic, which is going to be our pK1 for our C-terminus. It's going to be 2.18. We can draw a dotted line over from that to our 0.5 equivalents. We draw this point, and this is going to be our pK1 equals 2.18. Now we do the same thing for our next most acidic, which is going to be our pK2, our N-terminus. This is going to be about 8.95. We draw a dotted line over from that. And now we're drawing this to our 1.5 equivalents, because remember, this is going to be when we're at this state where we're talking about the pKa for this N-terminus group here. It's going to correspond to this 1.5 NaOH equivalent. And so we can go ahead and we can sketch that point in. And this is going to be our pK2 is going to equal 8.95. Now, finally, we're going to take our third pKa value, this time our pKr. This is going to be 10.53. You can draw a dotted line over from that to our 2.5 equivalents. And here we can plot that point. And that's going to be our pKr is going to be equal to 10.53. Remember, we have our buffering zone right around it, so we're going to kind of have a flat region around it. And now we want to find the steepest point. We want to find the inflection, the steepest point, the inflection point, like our equivalence points. And so this is going to be halfway between the 2 points, so halfway between like your pKa's on either side of it. So we can go ahead and we can take, for this first one, we're going to find the average of 2.18 plus 8.95 is going to be 5.57. So now what I'm going to do is I'm going to go over to 5.57 over here, draw a dotted line, come up over here, and that would be 5.57. But this is not going to be our PI in this case, because if we look and see what the charge state is here, well, now we have our charge state of +1, and we said that the pKa, that the PIs, and we have 0. And if we want to talk about where we have 0, well, this is actually going to be where we have 0. This is going to be our PI, not where we are now, but it is one of these equivalence points. So it's our equivalence point for our carboxyl terminus. Okay, so now let's go ahead and let's do the same thing for in between our pK2 and our pKr. 8.95 plus 10.53 divided by 2 is we get 9.74. So we can go ahead and we can come over to here, draw a dotted line over to our 2 equivalence points. And that would be our 9.74. And in this case, this is our PI. So this is going to be the average of the 2 closest pKas. And this is going to be our PI. This is the point at which we have a charge of 0. So this is going to be our PI. And that's going to be equal to 9.74, which is the average of 10.53 and 8.95. Now all that's left to do is go ahead and actually sketch our curve. So can unite those buffering lines, the buffering region, steep line through that inflection point. And then you have your buffering region, another steep inflection point, and your buffering region, and then another steep inflection point. And this would be how you would draw a titration curve for something like lysine. Let's go ahead and let's just label each of these different points. So we'll call this our A, B, C, D, E, F, and G. So this would be our A, our B, our C, our D, our E, our F, and our G. And now we have our titration curve and we're ready to answer questions about it if we need to. Finally, let's consider an acidic amino acid. And so we'll consider glutamate for this example. If we look at glutamate, well, now remember we're going to have 3 ionizable groups. So that's our answer for number 1. We have those 3 ionizable groups because we have the N-terminus, the C-terminus, and our R group. Remember, if we're talking about an acidic amino acid or an acidic R group, we're talking about in the neutral form, it acts as an acid and it can deprotonate. When it deprotonates, it's thus going to have a negative charge. So we're going to need 3 OH minus equivalents in order to deprotonate all 3 groups. So we can go ahead and we can draw our x-axis extending to 3. And remember, we're going to want to put our 0.5 increments. Okay, so now let's go ahead and let's sketch out what's happening at each of these different, points. Remember that we're going to go in order of increasing acidity. So in order of increasing pKa. So what is going to deprotonate first? What's going to deprotonate second? And what's going to deprotonate third? If we look to our pKa values, we can see that our N-terminus has the lowest pKa. It's going to deprotonate first. And then we're going to get deprotonation of our side chain, which had a pKa of 4.25. And then finally, we're going to get deprotonation of our N-terminus with a pKa of 9.67. And we can go ahead and we can sketch this out using our little shorthand notation. So if we're in our fully protonated state, we're going to have our N-terminus be positive, we're going to have our C-terminus be neutral, and we're going to have our R group be neutral. If we go out to 1 NaOH equivalent, now we're going to have deprotonated our strongest acid, so our backbone carboxyl group, but our side chain is still going to be protonated and thus neutral, and the N-terminus is going to be protonated and thus positive. If we go up another equivalence unit, now what's going to happen is we'll also have deprotonated that's our group. So we have a negative charge there as well as our carboxyl group in the backbone, but our N-terminus is still going to be protonated and thus positive. Not until we get to 3 NaOH equivalents is it when we get deprotonation of that N-terminus, which is going to make it neutral. And then you have the other 2 groups are going to be negatively charged. Thinking about the halfway points between them, at 0.5 equivalents, what we're going to have is we're going to have half of the C-terminus be protonated and half of it be deprotonated. When we go to 1.5, we're going to have, that is all going to be deprotonated now. But now your side chain, half of it is going to be deprotonated, and your N-terminus is still going to be protonated. You go out to 2.5. Well, now all of that side chain is deprotonated. All of that carboxylic acid in the backbone is deprotonated. And now half of your N-terminus is also deprotonated. So we have all these different states, and now let's actually draw what would the charge be at each of these points. On a pause the video and go ahead and write in all those charge states. Okay, so when we're fully protonated, we'll have a charge of +1. If we go up to 1 equivalent, we're going to have a charge of 0. 2 equivalents, we'll have a charge of -1. And 3 equivalents, we're going to have a charge of -2. And the halfway between those, we're going to have the half charges. Because remember, this is going to be corresponding to saying like, okay, well, there's half of it be protonated and half of it be deprotonated at the corresponding site. So this would be plus 0.5. This would be our minus 0.5, and this would be minus 1.5. Now we're going to go ahead and plot things out. In order to be able to do this, I'm kind of going to smooth things over a little. So hopefully you have more room on your paper than I have on my screen. But basically we can go ahead and we're going to plot these. And so what's the first thing we're going to do when we're plotting? Well, we need to basically plot out where those pH intersects our pKa. So we're going to take our first point, take our strongest acid. In that case, it's going to be our backbone carboxylic acid group with a pKa of 2.19. Going to go over to 2.19 on my y-axis, go over to 0.5 equivalents on my x-axis, and draw a point. This is going to equal to our pK1 is going to equal to 0.19. Now let's go ahead and go to our second strongest acid. In this case, it's going to be our backbone, our pKr, which is going to have a pKa of 4.25. So I'm going to go over to 4.25. I'm going to come all the way over to 1.5 equivalents, draw my line, and draw my point. And this is going to be my pK2 equals 4.25. Now, finally, I'm going to take that third pKa for our N-terminus, 9.67, come up over to 9.67 on my y-axis, draw a dotted line over to 2.5 equivalents, and plot this. Sorry, that was my pKr. This is going to be my pK2 equals 9.67. Okay, now I'm going to draw my little line around each of these to represent the buffering zone where not much is going to happen if you add a little acid or base, pretty flat region. But then remember that halfway in between these points are going to be where we get our equivalence points, where we have that steep inflection point. And we can find the pH at which this is going to happen by just averaging the pKa's on either side. So for our first pair, we have 2.19 plus 4.25 divided by 2. That's going to give us 3.22. So I'm going to go over to here, 3.22, kind of come over to here and sketch that out. 3.22. For the next one, 4.25 plus 9.67 divided by 2, going to give us 6.96. Okay. So now one of these is going to be our PI. Which is it going to be? Remember, what does the PI correspond to? The PI corresponds to the point at which we have a net zero charge. If we look back to our little sketch, where does this happen? Right, the PI is going to be where we have a charge of 0, which is going to be at this point. And this point is going to correspond to where we have, this point is going to correspond to where we have 1 OH equivalent. This is going to be our PI here. And so it's going to be the PI, we can find it mathematically by taking the average of our two closest pKa's. In this case, our pK1 for a carboxylic acid in the backbone, which was 2.19, and our pKr for the side chain carboxylic acid, which was 4.25. So this is going to be our PI here, which is going to be equal to 3.22. So I can go ahead and I can label this as my PI. And now I just need to kind of sketch things out, connect those lines, steepest point through those inflection points, flattest points in those buffering region, about 1 pH unit above and below the pKa, and then we have something like that. And voila, we've got our titration curve for glutamate. And we can go ahead and we can label these A, B, C, D, E, F, G, which would correspond to A, B, C, D, E, F, G, where we have our C is going to be our PI. So that's the basic strategy for drawing your amino acid titration curves. First, identify the number of ionizable groups. You're going to have at least two. You're going to have your N and your C-termini, possibly your a third group in your R group. And that's going to be the number of OH minus equivalents needed to fully deprotonate it. You're going to then draw your x-axis to extend that many OH minus equivalents. You're going to label each 0.5 increment, because remember, the 0.5 increments is that's where we're going to have the value where the pH is going to correspond to one of our pKas. In order to help see which of these it's going to be, we're going to sketch the state of each ionizable group at each increment and label its charge. So we can use a shorthand notation that's kind of like this. And when we do this, we need to remember that those zeros are zeros and not O's. So that's representing zero charge. Here we're representing zero charge. And we need to remember that we're going to deprotonate in order of the increasing pKa. Once we do this, we can then plot the points intersecting each half OH equivalent. So like 0.5, 1.5, or 2.5 if applicable, corresponding to where the pH equals the pKa. So that would be where we're going over to our pH, and we're going to draw a dotted line over to that many OH equivalents, dotted line down. That will be where we're drawing our point. We're then going to draw a flattish buffering zone around that point, and draw points at each of the full equivalence points where we're going to have that steepest inflection point, which is going to be at where the pH at those points is going to be halfway in between the pKas on either side of it. And in one of those cases, it's going to be a special place. It's going to be the PI, the isoelectric point. This is where you have a net neutral charge, and it's going to be the average of the two most similar pKas. And then finally, the titration curves are great for some things, and they're great for seeing what's going on. But if you want to know the actual proportions that are protonated or deprotonated, especially if you're in between, you're not at like a distinct number of equivalence units, you can use the Henderson-Hasselbach equation to compare the pH and the pKa to see what proportion is going to be protonated and what proportion is going to be deprotonated at any given pH. So I hope you're prepared to do a lot of practice problems with these, and hopefully you can see that it's really not as bad as it seems like it would be. And that for practical purposes, we're not actually going to use titration curves that much, but we are going to use our Henderson-Hasselbach equation, so we'll get lots of practice with that as well.